All right, this is a video for Unit 11, Day 5, and as always, we want to start with a warm-up. Sure, we're recording here, looks good. Okay, so this is a warm-up of the other video that I had you watch the other day. I want to solve algebraically. It's the whole method of common bases. So if I look at 1/16 and 64, what's the common base between 1/16 and 64? Hopefully you're saying the common base is, actually there's two answers. You can use a common base of 2, or you can use a common base of 4. Let's go with the common base of 4. So if I use a common base of 4, then 64 is 4 to what power? Third. And 1/16, remember, I'm really just thinking about the 16. 16 is 4 to what power? 4 squared. So this is the same as saying 4 squared raised to the x plus 1 power. But since it's a fraction, we can't just say 4 squared, we have to say 4 raised to the -2. Okay, good. So now we've got common bases. So what's next? Distribute the exponents. So we've got 4 to the -2x minus 2, because that -2 is multiplying both of those, equals 4 to the third. Once we have common bases, we can set the exponents equal. So -2x minus 2 equals 3. Add the 2, -2x equals 5. If I divide by -2, I end up with a final answer of x equals -5/2. Now I did that by hand because it said solve algebraically. The next one says solve graphically. And as of right now, the only way you know how to solve it is graphically. How come? Because you can't get common bases. There's no way to rewrite 5 and 1/3 using the same base like we did in the last one. So if I'm solving graphically, there's two options. I could do y1, y2, calc intersect, but remember what I said the other day, if you've done that homework from day 3, it's easier if you compare to 0. So if I do 5 to the x minus 1/3 to the x minus 1 equals 0, then it's going to be easier if you plug that into y1, that into y2. I actually do have a calculator today, so I can do that. So we're plugging y equals, that left side was 5 to the x minus 1/3 to the x minus 1. So 5 raised to the x minus, in parentheses, 1/3 raised to the x minus 1. And in y2, we want to put 0. I'm going to go zoom standard, and you're going to see that first some kind of weird looking graph is going to come through eventually. There it is. And then y2 equals 0. It's going to come through right there. Now remember, the reason I said it's better to compare it to 0 is because then I can just look for where it's crossing the x-axis. So let me go second calc intersect, first curve, second curve, guess. We've got 0.4056, comma 0, and I think it said to how many decimal places? 4. So 0.4057. Remember, if you're solving something graphically, what work do I need to see? The graph. So the graph, just need a quick sketch. Looks something like this. This is the point, 0.4057, comma 0. So we get that x is about equal to 0.4057. Okay, so again, if you haven't done the homework from day 3 yet, make sure you go online, watch the video for that, and get that taken care of. But that's a quick review or overview of what we did on that day. Today we're doing something a little bit different. And hopefully you all have this worksheet in front of you. This is Unit 11, Day 5. Today we're talking about applications of exponential functions. Okay, now, first off, when quantities increase or decrease by a fixed amount, we model that with a linear function. And we've done that already this year. Linear functions, you know, are the equations y equals mx plus b. And what's the shape of a linear graph? It's a line. And we talked a little bit about yesterday that that's also, we could think of a linear function as an arithmetic sequence, because you're going up by that common difference, that constant amount every time. But now we're really looking at quantities that increase or decrease by, instead of a fixed amount, like always plus 5, plus 5, plus 5. So for example, if I've got x is -2, -1, 0, 1, say -2 is 5, I'm just making this up. This is 10, this is 15, this is 20. I'm always going up by plus 5. So this is a fixed amount. In the past, we've called it a common difference. But if it's always increasing by the same amount, we say it's arithmetic, or that it's a linear family of functions. The difference with exponentials is that we're now increasing or decreasing by a fixed percentage. So the actual amount of increase is a little bit different. So let's say my x values are -2, -1, 0, 1 again. But now I'm going to be increasing by a fixed percent or a ratio. And that ends up looking like, if I multiply by 2 every time, if that's 2, then this would be 4, times 2 again would be 8, times 2 again would be 16. So here I'm increasing by a fixed percent. I'm multiplying by 2, I'm kind of increasing by, I'm doubling, so it's a 100% increase. I'll talk more about that in a minute. But it's a fixed ratio. That's a geometric sequence, or in function worlds, it's an exponential function. And those are the functions that we're really interested in this unit. Okay, so all of that to say, exponential functions, we wrote some equations of them yesterday. I'm going to change that equation a little bit. Yesterday we used y equals a times b to the x, which is the general form of an exponential equation. I'm going to change the letters slightly today. Instead of a, we're going to have a p out front. I talked about this really briefly yesterday, but that b, that fixed ratio that I'm going up by, I'm going to write as 1 plus or minus r. I'm going to use to the t today because you could use x, but t represents time, and a lot of these applications are going to involve time. So it's similar to the equation we did yesterday, but a little bit different. If you remember from yesterday, that number out front, that a value, that was the amount that we had when x was 0. So this number out front, p now, is still the same idea. It's the initial amount. That's what I start with. That r value, which came up really briefly yesterday, is the growth or decay rate. It's a growth rate if it's plus r, and it's a decay rate if it's minus r. Those are your major variables. The rest are kind of like your x and y. So t is kind of acting like your x, and that's usually going to represent time. A is kind of like your y. That's going to, if p is your initial amount, a is going to be your ending amount. Might be an amount of money, might be amount of people in a population, different things like that. And you should come to expect that these graphs are going to look usually something like that. Those exponential graphs that have a horizontal asymptote somewhere. Okay, so that's the background. Let's see what some questions are going to look like. So here's number 1. An exponential model for the population P in millions of Indonesia during the 1980s is given by this formula here, where T stands for the number of years since 1980. So first off, let me just show you how this relates to that equation that I showed you a second ago up here. This equation down here, A equals P times 1 plus or minus R to the T. You can see that my initial amount is that 148 number. R is contained in here somewhere. And they use P over here, but that's going to be my ending amount. So sometimes it helps to analyze this. What does P stand for? Well, first off, P is acting like your Y value. And that means the population. in millions. And t is kind of acting like where x has normally been. What does x stand for? Or what does t stand for? It's years, but it's more than just years. It's years since 1980. So that's going to be important in a second, because if x is 1, that means I'm talking about 1981. If x is 12, I'm talking about 1992, etc. So it says, in that decade, what was the annual growth rate of Indonesia's population? So here we're looking for that R value. So I got to figure out that R value is trapped inside this parenthesis here. And that parenthesis represents 1 plus R. So 1 plus R is equal to 1.021. And if I solve that little mini equation, subtract 1 from both sides, you'll get that R is equal to 0.021. Now, if I want it as a percentage, that means it's got a growth rate of, multiplied by 100, 2.1%. Part B says, what was the population of Indonesia in 1980? Now, anytime I've done word problems in the past, I've always done these want-when statements. And if you take the time to do that, I really do think that helps you analyze these a little bit better. It says, what was the population? So do I want like an x value or a y value, or a p value or a t value? Well, it's asking for the population, so clearly I want p value, the population. So I want p when what happens? Well, I'm given a time, a year, 1980. And since t is years since 1980, that would mean it's when t equals 0. So if you plug 0 in, you get p equals 148.7 times 1.021 to the 0. Now, you shouldn't really need a calculator, but if you do, you could just type in, all in one step, 148.7 times 1.021 raised to the 0. And you're going to get that number right out front. Remember your units, this is population in millions. So it's not really 148 people, it's 148.7 million people. Now, since t was years since 1980, that's also like our initial amount. So it shouldn't come as a huge surprise that that's the same as that initial amount value out here. Okay? C is similar. What was the population of Indonesia in 1987? What do I want this time? It still says what is the population, so I want P. And I want P when what happens? Well, when I'm in 1987. So that means T equals 7, because it's 7 years since 1980. So I'd have P equals 148.7 times 1.021 to the 7th. And this one you definitely want to plug into your calculator. 148.7 times 1.021 raised to the 7th gives me 171.98. Didn't really tell me what to round it to. I'll always tell you on a test for the regions. We'll say this is about 172 million. Okay, last part of this one. About how long will it take for the population to reach 170 million? Now the question says about how long. What type of variable am I looking at, P or T? How long is the time? That's years. So now I want T, and I want T when what happens? When the population is 170 million, so when P is 170. Okay, so if I plug that in, I'm going to have 170 equals 148.7 times 1.021 to the x. Okay. So now this, we don't know how to solve when there's a variable in the exponent if I can't get a common base. And it's not looking too promising between 170 and 101, 1.021. So if I don't know how to solve something algebraically, how do I solve it? Graphically. So how do I solve something graphically? We've been doing this all years. Put this into y1, put this into y2, calc intersect. Now the problem here is we're going to have to do a little finagling with our window. So in y1, here's 170, y2 is 148.7 times 1.021 raised to the x. If you just hit zoom standard right now, you're not going to see much of anything because these numbers are so big. So I'm going to have to adjust my window. Now the hint is this y1 of 170. I definitely have to see 170, and that's a y value. So what I would do is I would go to window. I'd make your y value at least 170, and as a good rule of thumb, I like to double it. So double 170, what's that going to be? It's going to be 340. Leave everything else the same for now. Hit graph. There's the 170. Now I'm looking to see where this line shows up. And if I see where it intersects, I'm good to go. And I think I am going to see it. It's going to happen right about there. So then I go my second calc intersect. First curve, second curve, guess. We have an intersection of 6.44, comma 170. So we need to show a picture of the graph. The window we changed, we went up to 340 up here. This is still negative 10 to 10, and this is still negative 10. And this was 6.44, 170. So about how long? We wanted the t value, or the x, that's about 6.4 years. But when would that actually be? Well, it'd be sometime within 1986, because 6.4 years after 1980 is 1986. Any questions? Good, I hope not. Here's number 2. Patient is given 150 milligrams of penicillin. Each hour H, the amount of penicillin A in the patient's bloodstream decreases by 15%. Part A, determine a function that gives the amount of penicillin left in the bloodstream after H hours. So the hint here is since it's decreasing by 15%, that's exponential. And we can write an exponential function with a percentage rate by using the equation A equals P 1 plus or minus R to the T. So really what we need to do is we need to figure out what P is and what R is, because then we'll have our equation, because A and T are just like X and Y. So what's P? What's our initial amount? 150 milligrams of penicillin. What's R? It's decreasing though, it's decreasing by 15%. So then R is going to be negative 0.15. So my equation here is A equals P times 1 minus 0.15 to the T. And I can actually plug in for P also. A equals 150 times 1 minus 0.15 to the T. We can clean that up a little bit too. A equals 150 times 0.85 to the T. Now one thing I get a little lazy about is leaving these A's and T's. You really got to be careful because the Regents will take off for that. They want the amount remaining to be A and the number of hours to be H. So we're going to have A, that's okay, equals 150 times 0.85 to the H. And that's really our answer. Now we can use that equation to answer these two questions. How much penicillin to the nearest tenth is remaining in the patient's body after 4 hours? What do we want? Do we want the A value or the H value? We want the A value because it's how much penicillin, that's an amount. When do we want it? We want it after 4 hours. So since H is in hours, I don't have to worry about units, H is just 4. So this is an easy plug-in. A equals 150 times 0.85 to the fourth. Go to my calculator, type it in all in one step. So 150 times 0.85 raised to the fourth, and I end up with 78.3. So it said this one did specify to the nearest tenth, so it's about equal to 78.3 milligrams. Then it says, how long to the nearest tenth of an hour does it take for 20 milligrams to remain in the bloodstream? What do I want now? The question says, how long? So I want a time. I want the H value. When do I want it? I want it when there's 20 milligrams, so when the amount A is 20. Plug that in, I'm going to have 20 equals 150 times 0.85 to the H. Now how am I going to solve that? Don't know how to do it algebraically yet. You will in a couple months. But I can't get common bases with 20 and 0.85, so we're going to do the old y1, y2 calculator sets. So here's y1, clear out what we got, 20. y2 is 150 times 0.85 raised to the x. Always reset your window. Go back to Zoom standard again, because we don't know. We might have to go to 340 this time. But I do see nothing. And that's because I'm looking for where it hits the line y equals 20. So what should I adjust in my window? Remember, that's my hint, this 20. That's a y value I want to see. So let's make y max equal to 40. So then I'll definitely have a good picture of y equals 20. There it is. And then I'm going to be looking for this graph to hit it, so I can find the intersection. And it should be coming shortly. There it is. It doesn't quite hit it. So now what do I need to change? Well, I need to go this way more. So now I need to change my x max. It's 10 right now. Let's just say we make it 50. That should give us more than enough room. It looked like it wasn't too far away from hitting it. So there's the 20 line again, and then we'll see the graph come through. There it is. We definitely got it now. So I can do second calc intersect. First curve, second curve, guess. It's like 12.4-ish. This is the nearest tenth of an hour. 12.4 comma 20. Make sure you show me your graph for the work. Just 12.4 comma 20. So to the nearest tenth of an hour, we got about 12.4 hours. Remember on your graph, the Regents does really like to see what you changed in the windows. We changed y max to 40 and x max to 50. So that's the window I'm looking at. All right, still doing okay, I hope? Okay, so let's do a money example on the next page. Let's see how we're doing time-wise here. Okay. Number 3, suppose you deposit $100 into an account that earns 5% annual interest. So there's that percentage again. So we know we're going to use that A equals P times 1 plus or minus R to the T. If I need to make a formula for this, because this asks if no withdrawals are made, how much money is in the account at the end of 4 years, if the interest is compounded annually, I need a formula to figure that out. So we better make a formula for it. What do you think my P value is going to be? And that's the initial amount you deposit. That's 100. Where's this 5% going to get factored in? That's your R value as a decimal, so 0.05. So I'm going to have A equals 100 times 1 plus, because I'm earning money, 0.05 to the T. Clean it up a little bit, 100 times 1.05 to the T. Doesn't specify any variables like the last one did, so A and T are fine. How much money is in the account at the end of 4 years if the interest is compounded annually? Now, I'll come back to this in a second. It just means I'm adding this 5% in once a year, which is what this formula is describing. So what do I want right now? I want how much money is in the account. That's an amount. I want A when what happens? The end of 4 years, so when T is 4. So this is just a plug-in. A equals 100 times 1.05 to the 4th. Go to our calculators. Put in 100 times 1.05 raised to the 4th. And it's money, so we always do nearest cent unless it says otherwise. So $121.55. Now this is where it gets a little tricky. The exponential function that we've been using when applied to investments represents interest compounded annually. Compounded just means how often the interest is added in. Annually means once a year. So the interest is added at the once of every year, like we did in part A. If you have a bank account, though, normally you don't get just interest added once. It gets kind of divided up throughout the year and then multiple times added in. So for example, if our annual interest rate is 5% is compounded monthly, then how many times per year do you think it's getting added in? Obviously 12, because it's every month. But you're not getting 5% in January and 5% in February and 5% in March. You're getting 5% over the course of the 12 months. So each month you're getting 5 divided by 12%. It's dividing up that from the number of times that I'm actually adding the interest in. And you're getting that interest rate 12 times in 1 year. So if I wanted to see how much was in the account now, I would still use a similar idea, but now my rate is 0.05 divided up by 12 months. So now A is going to be 100 times 1 plus 0.05 over 12. And it's also not just 4 anymore. So after 4 years, I'm not getting this rate added in only 4 times. I'm getting it added in 4 years, 12 times each year, because it's monthly. So the number of times I'm really getting this interest is 12 times 4. And that's because total number of times interest is added is 4 years times 12 months per year. So really I'm getting this 0.05 over 12 rate 48 times in 4 years. Okay, so now if I plug all of that into my calculator, you gotta be a little careful how you do it. It's 100 times 1 plus 0.05 over 12 raised to the, it's a good idea to put the exponent in parentheses unless you multiply it out in your head, 12 times 4. You should be getting $122.09. Now why is this slightly different? It's close, but this way I'm getting a little bit more money. Any idea why? I'm getting the same interest rate because I'm just taking 5 divided by 12 and then doing it 12 times. So over the course of the year, I get that 5%. But my interest added in January is earning interest in February. So it's kind of compounding. That's where that word comes from. I'm earning interest on my interests. And it's not a huge difference, but it definitely is to your advantage to have it compounded more frequently. So here's this last formula. In general, if you deposit P dollars into an account with an interest rate of R, compounded N times per year, and the amount in your account is going to be A equals P times 1 plus the rate divided by the number of times compounded, so R over N, it was compounded 12 times in our last example. And it's not raised just to the T anymore, it's raised to the number of compoundings per year times the number of T years. So we need to use this formula whenever you're dealing with money that's compounded a certain number of times. So when you're doing your homework, look for questions that say compounded. Know to use this formula as opposed to this one that we used when it's just a constant rate per year. Okay, so real quick at the end here. If no withdrawals are made, how much money is in the account at the end of 4 years if the interest is compounded? Only thing I'm changing is how often I'm compounding. Any idea what N would be if it's semi-annually? Semi means twice a year, so N is 2. So we'd have A equals same values from before, so 100 times 1 plus 0.05 over, and now it's over 2, raised to the 2 times, we're still talking about 4 years. If I plug that in my calculator, that's be about $121.84. So still slightly more than once a year, but not as good as 12 times a year. If it's compounded quarterly, what do you think N would be? There's 4 quarters in a year, so N is 4. So 100 times 1 plus 0.05 over 4 to the 4 times 4. That time your calculator will give you $121.99. So again, slight improvement in the number of more times I compounded per year. What if I did something crazy and got interest added every single day? What would n be? 365. So a is 100 times 1 plus 0.05 over 365 to 365 times 4. That rockets you up to 122.14 cents. Still more, but not all that much more for that big of difference in how many times I compound. Okay, how about hourly? How many hours are in a year? Well, if you figure out 24 hours in a day times 365 days, we got 800,760. I'm not talking about leap years. Don't worry about that. So A is 100 times 1 plus 0.05 over 8760 raised to the 8760 times 4. And crazily, if you do that in your calculator and round to the nearest cent, it's the exact same as before. It's not really the exact same, it's just that it's a big long decimal, and the decimal's changing way lower than the hundredth place. So you can see, as I increase compounding, the amount of money I earn is increasing, but it's leveling off. And eventually, what is it leveling off to? Well, if I could compound an infinite amount of times a year, we call that compounding continuously. Every moment in time and then some. So essentially n equals infinity. Well, I can't plug infinity into a formula, so how do I deal with that? That's to be continued. It's coming soon. But as a preview, think about what's happening. Annually, I earned $121.55. Semi-annually, $121.84. Quarterly, $121.99. I'm still growing, but I'm growing less and less. I'm reaching a certain level that I'm not going to overpass. What's that called? I'm reaching an asymptote. Where that asymptote is will be coming in a couple days. Okay, so that's the end of the lesson for today. Hopefully it wasn't too confusing. You should have a worksheet, or you'll be getting it shortly. Please do the best you can with that. Check your answers on the answer key as always. I'll be around to ask questions after school today, or whenever you can find me. So good luck with that. See you.